correct, they went and stated that AMOC has not changed significantly over the past 60 years or so.
That was
And
it.
now,
Hmm.
well, hang on. So now the question becomes, what constitutes a significant change in AMOC? This has to be. It's not
Great
defined.
question.
It needs to, because here AMOC is collapsing, AMOC is slowing, it's doing this, it's significant. What constitutes, one, a slowdown, two, a significant slowdown, and what's meant by collapse? Does collapse mean total stoppage?
Yeah.
Well, I think we know what. I think we will know when that happens. We'll actually be able to. Oh, there's no more sinking at all.
We'll be
Okay,
dead.
we have a stoppage.
Hmm.
Okay, we have a stoppage. So they didn't put it in the paper. So what the graph that you're showing up there
Hmm.
is one I created.
This one.
I went into
Okay.
the yeah, I went into the data, and I took all the AMOC values that they reported. They
Over the
have
60 years. Yeah.
yeah, they have like a supplemental thingy in the paper. So I went and
Okay.
took that and I
All
plotted
right.
it. And I plotted it. I fitted a linear regression line through it,
This one.
and
Yep.
yeah, right. You can see the little dotted line right
Yep.
through here.
Yep.
And then I put a little panel in here showing the equation. And hang on, I got to kind of tear into this a bit. The equation is y equals, I'm just going to say
Zero.
1.85,
Okay.
1.85 times 10 to the negative 3x minus basically 3.6. I'm just doing some rounding.
Okay, guys.
Okay.
You got that because it's going to be on the test.
Okay. That's not the important thing. Okay.
Yeah.
There's your fit equation. The important thing is the p-value. You see the p-value of 0.12. What is that p-value referring to? That p-value is testing the coefficient for x. In other words, is the coefficient for x that gives you the slope of the line, right? Remember from basic high school algebra,
Oh,
y equals
God.
mx plus b, right?
Yeah,
Right?
100 years
Remember
ago.
that?
Yeah, barely.
Right? Where m
Yeah.
was the slope, b is the y-intercept.
Yes,
Okay,
yes, yes.
so the slope here is that 1 point times 10 to the minus 3. That right?
Yep.
That's your slope.
Yep.
Okay, so the p-value here is testing, is this slope, is this coefficient for x, which represents the slope, does that significantly differ from 0? And when you get a p-value of 0.12, and if you're testing at the 95% level, then
Hmm.
the critical value is 0.05. If you're testing at the 99 level, then the critical value is 0.01. In other words, a value less than either 0.05 or less than 0.01 would tell you have a significant result. Well, 0.12 is greater than either of those values, which means we have an insignificant result, which means that, in essence, this line does not differ from 0.
This line.
This fitted line, the little dot dash
Yeah,
line there,
it doesn't
does
differ
not
from zero, even though it
does not.
does look like.
Yeah, I can change the scaling on that, and that thing will be flatter than a board.
I got ya. Nope. Now I understand the anomalous. Okay, and these points are the 60 years of
Yeah, those points
measurements.
are the 6 year. So
Yeah. Of
basically,
the.
when you test for the significance of
Yep.
the coefficient, what
Hmm.
the null hypothesis is that the slope of the line does not differ from 0. The alternate hypothesis is that it does. Here in this case here, we have to accept the null hypothesis
Hmm.
that the slope is not significantly different from 0, which means you have a flat horizontal line. That's what
And
this
that
tells us.
and it tells us really then what the paper was all about. The 60 years, it has not significantly changed.
It has not and that's what they're saying.
And
And
these are variability points. The
the
anomalies are just where
yeah,
it
and if you look at the R square value, the R square value is really not great. It's like 0.05 or something like that. So the R square, which means it's kind of all over the place.
I see.
So
60 years of all over the place. However, Jim, let me ask you a question then. 60 years of all over the place, pre 1960, was anybody measuring this, or would it have to be retroactive in time models?
Well,
I mean, did
well,
anybody know how to do this? Were scientists hip to this?
what are they doing? They said they looked at proxy data. They went back to
Prox.
1850.
That
So they
was in
took
the other
proxy
one.
data.
Okay.
That's what this whole paper is based on, proxy data.
Okay. All right. It's all proxy data because I know
And
here, but
whatever they have measurements for, plus plus using proxy data
okay.
to
Okay.
reconstruct what happened in the past. But that's that's what they
Gotcha.
stated. They used proxy data plus
All
this here,
proxy data.
and whenever we do climatology,
Mm-hmm.
we're using proxy data.
Right.
When we say, if you, oh, what's happened in the Younger Dryas, what's happened in this, we're always using proxy data to reconstruct past climate situations.
Exactly.
So when they say that we state that AMOC has not slowed significantly, they're basing it on this here,
Yes.
and their data is correct. I wanted to show that, but however, if you look at this carefully, especially starting from around 1975-ish or so,
All right.
it almost looks like there's a wee bit of a sawtooth pattern there.
This right here.
The actual points themselves, it looks, it reaches
Yeah,
a,
look at
a,
that.
a high value, then it comes down, it goes back up, it comes back down, it goes back up, wiggles a bit, goes back up, comes back down.
What would
It
explain
almost
that?
well, hang on.
Yeah.
It almost looks like this is cyclical. Well,
Oh.
we need to be very careful, because yeah, you may look like cyclical, but and we have techniques to determine signals and cycle
Mm-hmm.
in time series data.
All right.
We can use the Fourier transform, we can use the Fourier smoothing function, and so we can do that and then pick out any signals. And that's a common technique. For
Mm-hmm.
those who may remember their calculus studies, you probably were familiar with power series, where you explain functions through a series of exponential of excuse me of power function, like x to the something power, and a whole bunch of other x terms to a something
Yep.
power, like a Taylor or Maclaurin series. Fourier series are trigonometric series, and especially for sine and cosine, which tend to be cyclical. So the cautionary note here: while this may look cyclical, do not jump the gun, because the
But
last
it's
data point they
not.
have here is,
Right.
you never know. Hang on. You, you, let me go with my thought here. Because it goes up, it comes down, it goes up,
Yeah.
it comes down, it goes up, it comes down. Oh, that
Ooh.
sounds like a cycle. But
Yeah, you're right.
okay, what happens at the very last data point here? Does this continue downwards, or will it go back up? We don't know. If it does go back up, then an argument might be made where maybe this whole thing is cyclical. We don't know. We would have to apply the analytical techniques to do that. So, as a caution to, not to being to avoid the temptation of saying something cyclical, let's jump down to slide number 9 first. Then we'll come back to 8. Okay. You look at this here, and you kind of say, well, that almost looks like a nice cycle. 1 hertz or
Yeah.
something like that.
Go
It
up
almost
and
looks like
down.
almost like a sine curve. Well, in this case, it'd be negative sine if it were, right? It'd be tempting to say we have something cyclical going on here. Go to the next slide, number 10.
Oh.
That that number 9 slide issue, the one I just showed you,
Yeah.
is part of this overall function.
Okay. That's what I thought.
In other words, I cropped it at x equals -1 to x equals +1. And really what this is this function is f of x equals x³ - x. It's not cyclical at all. 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 It's not cycli It's not cyclical. We just have some interesting things going on here where we end up what's called a relative maximum and a relative minimum. But in this function here, as x goes to positive infinity, the function goes to positive infinity. X goes to negative infinity, so does the function.
So
So
there
this is
really,
why I say
yeah,
it's that's why I say you have to be cautious and not be
right.
tempted to say something cyclical. Okay. So now you have heard me say, whether on this podcast or in my video, that AMOC is slowing. We've been measuring the slowdown for the last 20 years or so, right? And if you look at the tail end of this graph here, it would, except for this one little, little burp
Little
upwards,
the
it would
burp,
it would look like it's slowing down, right?
right?
We've been right. Teams from Dalhousie and Halifax, Dartmouth, Nova Scotia, the Norwegian research, have all been measuring the slowdown. Anyway, it's slowing down. So what I did, and now this is slide number 8. What I did was I took these last data points here, and I ran a regression on those data points. And when you when you look at the regression
Oh,
just on that, okay, now take a look. We have
yeah.
the equation is y equals minus, because it's negative slope,
Mhm.
0.0672
Mhm.
x plus 135.4. But now look at the p-value, 0.00005. In other words, the slope does significantly differ from zero. We have something going on
Oh,
here.
that's pretty wild. Look at that. So you're looking at
And you,
the overall 60 years, and then you get close and you're looking at just the last several years or this chunk, and you see a difference.
and you see, and the R square is much better. It's 0.88.
Hmm. That's interesting, Jim. I see.
So now the question is, well, does this mean AMOC is significantly slowing? Well, if we accept that a significant slope is answers that yes, then yes, it is significantly slowing down.
From this
For,
analysis.
over the last 20 years.
Right. So what does that mean for everybody to understand?
We need more data.